Okay, it's 8:05, Wednesday the 13th of August. Moon is in the middle of the third quarter. The sun is set, and this is what our sky looks like. It's got a little bit of a silvery blue cast to it, but probably as good a sky as I've seen in quite a few weeks. Let's go have a look at 8,000 foot high Cannon Mountain to check out what the cloud and situation is up there. If the humidity is high, you'll see precipitation above the peak. And here we are at 3,000 feet high, John Day, Oregon. You can see I've already parked the scope at the zenith. Been watering the plants. I'm going to go ahead and turn that off. The grass, I'm going to go ahead and turn the water off. The pump. Here we go with the scope. I powered it up about a half an hour ago. I reset the time. And now what I need to do, and we can take a look at the balance level, which tells us a little bit of something about how the scope may be slightly out of alignment in its crib inside the housing. And let's take a look also at the bubble level here. Get another sense, pretty much centered up right there, not bad. All right, so I'm gonna drive the scope. I'll see, first menu, I think I already uploaded the model. Okay, I'm gonna do it again, and we'll double check to make sure that I actually save the model. I'm sorry, you can't see it. Save the model by looking at the parameters. Parameters are pretty tight to the east, and if I switch to the west, about the same, so it's got a pretty good balance. So my next step is to do a synchronization, and to do that I have to first go to a bright star, and an obvious one, let's say, is Altair, and now the scope will drive. Tonight, of course, I've got an observing plan in detail based on average brightness, which is the mathematical formula I'm using now to get a better sense of what I should and shouldn't be able to see in the eyepiece of a 6-inch scope. I am, of course, using the same equipment as last time. We have the 32 millimeter scientific Explore Scientific eyepiece with a 62-degree field of view, plus the 2x ED Barlow lens, fully multi-coated inside the 2-inch diagonal. I have a 50 millimeter finder scope with reticle, but the batteries run out and I don't use it anyway. And now that it's sunset, I should be able to see first magnitude Altair, Alpha Aquili, in the finder scope. After which I'm going to wait the requisite 45 minutes that you'd have to wait before beginning a Messier marathon, and pick out the first study of the evening, which is on our list here and is based on average brightness. I probably will not view Messier 13 because it's westering, but we will begin with NGC 6633, which has an average brightness even brighter than Messier 13 of 8.2 magnitudes. And as you may recall from previous videos, average brightness has to do with the size and the cumulative magnitude of any given deep sky study. So let's go ahead and remove the lens cap and do this synchronization. Okay, you may have seen this video, El Quattro Monoviewing by Moonlight, previously. Now, there's no imaging in this particular video on our Golden Phoenix Publish channel YouTube site. However, I do demonstrate various studies on a pad illuminated by an amber lamp. Now, I am not going to be using the 150 fast newt, which effectively reduces its aperture down to about 125 millimeter, especially when you add a Barlow lens, which splits the light, but losing 0.8 magnitudes through each eyepiece. But when you combine them both, again using your eyes, you add another 0.3 to 0.5. So effectively, a scope that ordinarily, if it were a refractor, could show stars at 150x 1 millimeter exit pupil down to magnitude 13.5 is effectively reduced because of the obstruction and the monoviewer at about 12.8 to 13.0 magnitude stars, and those would only be visible at 150x, this is roughly 60x, when directly overhead at night, and stars could be seen down to magnitude 5.5, or the Cygnus rift in the summertime was clearly visible in Cygnus, the Northern Cross, and the rest of the Milky Way shines quite brilliantly all the way down to Sagittarius. However, the last few nights of observing have not been that good. So that is the video that I have been adding some commentary on, but the commentary was not based on the 150 El Quattro fast newt, but based on the 6-inch 150 that I'm going to now read into this, and then I will add some other notes so that I have like 15 or 20 minutes of video that I can add captioning in after I get this next observing plan out. Oops, press the wrong thing. Read more. Okay, I have an OBS report from the 808, August 11, 2025, when the moon was pretty seriously hampering viewing, especially late at night in the summertime when sky dark doesn't arrive until about 9:45. So, on August 11, 2025, I set up the semi-epichromatic f8 150mm Eddy in Penty, the backyard observatory, which you have seen, with the 2-inch wide field 32mm plus 2x bar and 2x Barlow for 75x 2mm exit pupil in the late afternoon. I also threaded in a 2-inch Optolong deep sky filter to the Barlow. My basic goal was to begin with 50mm deep sky studies from the Astro Geek Joy Deep Sky Atlas, which I will show you in a minute, and progress as early in the evening as feasible. All right. Beginning at about 9:10 PDT, I was able to view Messier's 513 and 6, plus NGC 6530. That 9:10 time, I believe, was about a little more than an hour after sunset, so not quite sky dark. Beginning around 9:15 to 75mm scope optimized M92. Now what that means is M92 on a good night of seeing stars neighboring to 5.5 should show some resolution through a 3-inch scope. So should Messier 10 and 12, which was faintly viewed. 7, 24, 25, and NGC 6633 were all visible. By 9:23, moved on to 100mm space scope optimized NGC 6572, Messier 1662 for 8, 21, and 28. Beginning at 9:48, which would have been sky dark, but except for the looming Moonwash to the southeast, had flipped the scope east-facing to catch NGC 6818, 7009, 7027, and Messier 29. Views to deep south were hampered by poor eyepiece presentation. As I mentioned, I had to use my left eye. Of the various studies, Messier 12, NGC 6218, with data to follow, had an average surface, was the Vegas, so Messier 12 the Vegas. Later that evening, had a look for Galaxy NGC 6207 near M13. Data follows. Average surface brightness 13.1. Average brightness, which is a key concept here, of the cumulative magnitude 11.6 plus its average surface brightness per roundish arcment of 13.1 divided by 2 equals 12.35. And I have been able to see this at the eyepiece through a 150mm Maxitov. Not sure whether direct or reverted decades ago under dark sky conditions. Should be able to see it direct through Eddy once the Moonwash has left our skies. Stay tuned in comments to follow. Basically, NGC 6207 is the holy grail for 6-inch scopists. The question: through which quality skies, what lunar conditions, magnification, using direct vision, averted, or eye movement. Averted equals a 9-inch view, eye movement at 12, which adds 1.5 magnitudes to your visual sensitivity. Note, M10 was easily seen, also known as 6254, with data there, was far more present in the eyepiece than M12 as described above. What's the hap here? It'd be very interesting if there's some data problems because they are very close to each other in the sky. So we're going to cancel out on that. Okay, a brief read on the OBS report from last night on the 12th of August 2025. Had Eddie out as specified earlier. Did loads of pre-planning involving post-cometary deep sky studies. 30 degrees south is as far as I'll go to 45 overhead, and then we get obstruction from the observatory. This involved 25 studies, 9 of which were Messiers and 16 were NGCs. 8 of the Messiers were at the top of the list for average surface brightness, which I've already described. Brightest AB was M13, NGC 6205, and the faintest was NGC 6384, and that was a pure NGC. These were 8.9, 12.1 respectively in terms of their averaged brightness. So Messier 13 was 8.9 and NGC 6384 was 12.1. The near overhead M13 could just be held direct 30 minutes after sunset, which really is interesting because during a Messier marathon, you got to deal with Messier 31, 110, and 32, and they are very close to the horizon, and you have to be able to catch them about 45 minutes after sunset in late March, early April. Near overhead was NGC 6384, was barely held direct. That was a 12.1 average brightness galaxy. Well after sky dark, which occurs 90 minutes after sunset. All studies less than AB 11.0 could be held direct regardless of where found in the sky by sky dark. That list included Messiers 13, 92, 4, 62, 10, 19, 80, 12, and 107. The 5 brighter than Messier 107 as NGCs were also held direct. NGC 6235, 6304, 6356, 6293, and 6316. Because all such were visible at the eyepiece before sky dark, they were at least vaguely held direct against a slowly dimming eyepiece backdrop. Vaguely means they were clearly, obviously, somewhat, maybe brighter than the background sky. At no time did the eyepiece view look pitch black, even after sky dark. Just before, and that's typical of the 75X under 4 to 4.5 ULM conditions. Just before sky dark, all stars making up the Northern Cross could be held direct. I'm not sure of the magnitudes. I'm sure, now this is without my glasses on, so you can typically add 0.5 magnitudes, whatever is the faintest star in the Northern Cross. After sky dark, the Milky Way could be vaguely followed into Sagittarius, but the Cygnus rift was not visible. Skies can be estimated to have been 4.5 of 6.5 magnitude transparent. That's the typical range. 5.5 is the very best seeing I get here in John Day at 3,000 feet, and 6.5 I've experienced at 6,000 feet overlooking Crater Lake. That was a documented report on the astro.geekjoy.com website, which is no longer available. It may not even be able to find anywhere on the web anymore. The list of not seen NGCs progresses from NGC 6287, 6342, 6366, 6355, 6269, 6207, which is our bellwether for a 6-inch scope, 6325, 6166, 6181. The unsanes ranged from average brightness 11.1 to 12.35. While averted sight or eye movement is likely to have revealed all such, no effort was made to use the 6-inch scope to get 9 or 12-inch views by using either averted vision or eye movement. Averted vision typically adds 0.8 magnitudes to reach and eye movement 1.5. NGC 6309 and 6384 with average brightnesses of 11.5 and 12.1 were the exceptions. One is a near arc-minute sized planetary nebula. That was 11.5 AB, and the other a large galaxy seen in the sky's middle third, which magnitude was 10.6, but it covered a lot of space. Typically, galaxies in the 10th magnitude range do. This is something like 6 by 4, I think. Data on both, you can see it there. And you can go to the write-up on El Quattro Monoviewing by moonlight. Here are my conclusions. Low sky position easily loses 1 magnitude of AB to sight. Meanwhile, large, low, average surface brightness galaxies like 6384 can be vaguely held direct at 2 millimeter exit pupil, 75x through a 150 millimeter unobstructed scope. Anything above roughly AB 12.0 needs deeper seeing skies to be reliably held, and that depends on sky position. AB 12.5 or less should be seen in parts of the sky transparent to magnitude 5.5. 1 magnitude fainter on this occasion. AB 12.5 magnitude studies at 75x are 1 magnitude fainter than the stellar reach of such a scope operating at 1 millimeter exit pupil 150x. Keep in mind that Optolong deep sky filter helped correct for local municipal lighting, but such lights can and did have an effect on my dark eyes adaptation because it was constantly streaming in, though at a low level. Finally, even a deep sky filter, not a nebula filter, can distinctly reveal planetary nebula of reasonable apparent size. Down to 20 arc seconds are pretty straightforward. By the way, please visit Steve Gottlieb's Adventures in Deep Space website to research all studies, including this report, for further insight. If you do so and anything relevant comes up, leave a comment below. All right, one final read through. I have no idea why strike theories occur above. I mentioned that. Here are my rough conclusions and preliminary generalizations. A 50 millimeter wide field binocular, time that goes on a mount, or astronomical binocular operating at 25x 2 millimeter exit pupil should reveal any study having an AB, which is defined here as the average brightness, equals the cumulative visual brightness plus the average surface brightness per roundish arc minute divided by 2. And that value generally has to come out to less than 9.7. A 3-inch refractor should reveal any study of less than 10.5 AB. A 6-inch, you add 1.5 because you double 3 inches to get 6 inches. To get 12.0, you double the size of to a 12-inch scope because it has 4 times the area, adding 1.5 magnitudes to get to the 12.0, and you get 13.5. An 18-inch scope, you can add 0.8 to a 12 and you get 14.3. A 24-incher, 15.0. 36, well, that's half more. It's going to be 15.8. And assumed stars to magnitude 4.8 can be held direct, nominal, not optimal, nor excellent seeing, the kind of a night and barely be willing to do eyepiece astro under. Through better skies, add 0.5 magnitudes for skies to the upper limit of what you'd expect to see, when the Cygnus rift might be showing 5.5 magnitude stars should be seen direct near the study. For me, that's 5 without my glasses on. And 1.0 for whenever you banished all artificial light by observing at 7,800 feet on a high desert plateau. Meanwhile, subtract 0.5 for anything well placed but not in the sky's middle third. And that basically means when the sky starts to shift from being dark to being somewhat illuminated because the atmosphere is thicker, that's outside the sky's middle third. And then subtract another 0.5 for anything between 15 and 25 degrees above the horizon. Typically, I get decent views down to minus 25 degrees below the celestial equator from 45 degrees north. Anything below 30 degrees below the celestial equator, I don't even bother with. Of course, those 18, 24, and 36-inch views would likely be seen using an imager through a 6-inch scope. However, Steve Gottlieb has reported seeing at the eyepiece in some of his reports he describes what you see at the eyepiece of a 48-inch scope, typically in the 400x magnification range. Meanwhile, all bets are off when viewing anything smaller than 1 arcminute in size. That will require more investigation. Okay, now let me quickly review what I went through already. Last night I was looking to the south and overhead with the scope mount oriented to the west. Tonight I made a list oriented to the east. I will start with Messier 13 at a half an hour after sunset just to see what it looks like. I will then, and that has a value of averaged brightness of 8.9, so it should be reliably viewed and give a good view through those 50 millimeter 25x binoculars. Then we step down a little bit to NGC 6633. Probably, I don't know what that is. I don't list it here. I'd have to look it up. That's at 8.2, 6604 at 8.3. Then we move on to Messier 23, 6494, 9.1. Messier 18, 6613, 9.3, I believe. Then 6425 is a 9.5, 6626 is a 9.5, 6611 is a 9.6, and 6514 is a 6637, which is also Messier 69, is a 9.8, and then Messier 20, NGC 6514 is a 9.9. Once we get to NGC 6618, which is also Messier 17, we enter into the double-digit region, a 10 average brightness. 6624, 10.1, 6540, 10.1, 6402, 10.3, 6544, 10.3, 6553, 10.3, 6652, 10.3, 6681, also 10.3. Wow, what a spade. 6522 at 10.4, 6528, 10.9. Probably by the time we get to 10.9, we're going to need to have achieved sky dark. 6440 at 10.9. 6445 is a planetary nebula, smallish, 10.9, so it doesn't have an average brightness. 6642 at 11, 6694 at 11, 6638 at 11. 6453 at 11.3 average brightness, 6401 is 11.4, 6539 at 11.9, and the acid test will be NGC 6661 at 12.4. I also will look at Messier 57 to see if the 13.1 magnitude star can be seen at 75x. Typically it takes 150. I will look at Messier 27. I've had hints of the football shape of the dumbbell. And then I will go on to 6888, blew me away with the Optilon filter. Even the other night I could make out the Crescent Nebula. Astonishing. So that's the plan for tonight, and those notes will be used in sequence as the sky gets darker and darker, and I will include notes in the captioning of this video, but I will add those notes tomorrow. I'm going to go ahead and put this video up now, and I probably will not include all of the reading and discussion on tomorrow's video when I follow up using this study, but based not on the fast F4 Newt, but based on the F8 semi-apochromatic non-obstructed refractor that you saw earlier in this video. So, carpe diem, by day, and